So it's my pleasure to welcome Sharon Shoham from Tel Aviv University. She recently started as a professor there. So previously she got her PhD from the Technion in 2009. So Sharon's done a lot of interesting work in verification, model checking, abstraction refinement, and recently it's broadening her interest in distributed protocol synthesis as well. Also recently got this prestigious ERC grant, so congratulations. So yeah, please welcome Sharon. Go ahead.
Thank you. Thank you for the kind introduction. So I'm going to talk about interactive verification of distributed protocols. And I don't have much to say about motivation because I think the motivation is quite clear. We have distributed systems all around us. Nate talked in the morning about networks, which are essentially distributed systems. If you look at an autonomous car, then it has multiple processing units controlling different devices. So this is also a distributed system. So they are really everywhere. And unfortunately, they are very difficult to get right. And also testing for them is very, very costly and also not sufficient because of rare bugs that are often just left undiscovered. So we really need to verify these systems, these distributed systems. But unfortunately, verification is hard. When we talk about distributed systems, distributed protocols, they are essentially infinite state systems because we want to verify them for any number of nodes, and they typically use messages which are unbounded, and we have an unbounded number of objects that we should worry about. So this all makes it an infinite state system. And then we know that for infinite state systems, verification is undecidable, which makes our lives quite difficult. Now, if we look at the state of the art in verification, then we can roughly divide the existing approaches to automatic approaches like model checking and static analysis based on abstract interpretation. And these approaches are ultimately limited because of the undecidability. And on the other hand, we have the deductive techniques where a human user annotates the system or the program with some information that is relevant for the proof. And from these, we derive some verification conditions, which can be discharged using SMT solvers or interactive theorem provers in order to really carry on the proof. And these approaches are very successful, but they require quite a lot of effort from the user. If we look at the two approaches in comparison, then if we look at really deductive approaches based on proof assistance, then they are very expressive in the kind of, usually they are very expressive in the kind of proofs that they can come up with. But like I said, they require a lot of effort from the user. So for example, the recent work from University of Washington in the Verdi project reported that they needed 50,000 lines of proof to verify the RAF protocol, which is quite a lot. If we look at the automatic approaches, then they are very appealing because of the high degree of automation, but they are usually, they have limited expressivity, and they are ultimately limited by the undecidability of the problem. So each of these approaches has its own benefits and also disadvantages, and it would be really great if we could somehow go beyond the limitations of these approaches and find some sweet spot where we can enjoy both worlds. And this is what I'd like to do in this ERC grant that I received on supervised verification. And today I'm going to talk about some preliminary steps that we made in this direction in a tool called Ivy. And in Ivy, just to give you a sense, we managed to prove safety and actually more than safety, but today I'll talk about safety, but safety properties of systems. And we typically need something like 1/10 of a line of proof per line of code, which is much better than the ratio that you have when you use proof assistance. And with Ivy, we managed to verify various interesting protocols, like a learning switch from the domain of networks, and also we recently verified several variants of the Paxos consensus protocol, and I'll talk about it a bit later. And you should ignore the numbers for now. They are just meant to show you how much effort is needed from the user, but I'll get back to it later. So this is just to give a sense of the kind of protocols that we can verify. Okay, so now what do I mean by supervised verification? How do I want to find this sweet spot? So if we look at automatic verification, we can think of it as if we have the user who provides some description of the system, some model, and then we have the verifier, an automatic tool that automatically and independently tries to search through this huge space of potential proofs. And it does it all automatically and without approaching the user. And then the problem is that these verifiers sometimes diverge. They can often be unpredictable, and also they have a restricted expressivity, again, because of undecidability. So the idea in supervised verification is somehow to divide the verification effort between the automatic verifier and the user, make sure that the verifier only has to take care of well-defined decidable problems in order to make the whole thing predictable, not let the user wait and have the tool diverge. And then add a layer of interaction between the user and the verifier, and with that layer of interaction, let the user guide the verifier when the verifier needs some intuition, to get some intuition from the user, and in this way, also obtain high expressivity. And then the question is really how to do this division of work, what kind of tasks should we let the verifier take care of automatically, and what should be the role of the user, and also what kind of interaction should they have, in what form should they carry the interaction. And like I said, today I'm going to talk about Ivy and what we did with Ivy, and we have a series of works that we did with Ivy. Today I'm going to talk mainly about the first one, where we used Ivy to verify safety properties of distributed protocols. There is another work that I'm not going to talk about that is focused more on the expressivity, how we managed to obtain really expressivity. And we have a recent work that talks also about verifying liveness properties and actually arbitrary temporal properties in Ivy. But I'm not going to talk about it today, so this is what will be the focus. Okay, so we are now talking about safety verification of safety properties. So what are these? What are these safety properties? So in safety verification, we have some description of a system, and we have a description of bad states, some scenarios that should not occur, that we want to verify that do not occur in the system. For example, I will use as an illustrating example a leader election protocol. So in a leader election protocol, bad states are states where we elected more than one leader. Okay? And so we want to verify that no matter how many steps the system makes, starting from the initial states, it never reaches such a state, never reaches a bad state. And usually when we talk about infinite state systems, we cannot just compute the set of reachable states. So what we do in order to verify safety is come up with inductive invariants, or loop invariants if we are talking about loops. And what are these inductive invariants? So an inductive invariant is some property that has to be safe. It has to be disjoint from the bad states. It has to include the initial state, so satisfy initiation. And the most interesting property is that it has to satisfy consecution, which means that if we start from a state that satisfies this property and we make a step of the system, then we have to get back to a state that satisfies the property. And we should never have transitions like that start from a state that satisfies the invariant, but leads to a state that violates it. Okay? So now if we have these two conditions of initiation and consecution, together they ensure that this property, this invariant, is a superset of the reachable states. So it basically gives us a way to find the superset of the reachable states without actually knowing what the reachable states are. And we have these local checks that we can make in order to make sure that this is really a superset of the reachable states. And then if we also have the safety property, we know that all the reachable states are safe. So we proved the safety. Okay, so let's look at a simple example to illustrate this notion of inductive invariant, which is sometimes confusing. So let's look at this simple program. The program initializes x to 1 and y to 2, and then it has a while loop where we assert that x remains odd, and inside the loop we increment x by y, and we increment y by 2. Okay, and in this program, so I want to verify that this is really, that the assert always holds. And let's look at what happens when we really run this program for a minute, just to get a sense. And I want to emphasize that here I'm going to look at the entire loop body as one step of the system. Okay, so this is the resolution that I'm looking at. So the initial state at the beginning of the loop is that x is 1 and y is 2. And it's quite easy to see that this is the path that we are going to get if we are really executing the problem. So it's quite easy to see that x remains odd because we always increment it by y, and y is always even. Okay, so the program is safe. This is quite easy. But now let's try to prove it with an inductive invariant. So our first attempt for an inductive invariant can be just to take the safety property itself, the property that x is odd. Okay, let's see, maybe this is already inductive, and what do you think? Is this an inductive invariant that can prove the safety of this program? Okay, so help a bit. So even though really x remains odd in all the runs of the system, this itself is not an inductive property. Because, for example, this state where x is 1 and y is 1, this state is not really reachable. But still, it satisfies this candidate inductive invariant. And if we make one step, execute the loop body once from this state, then we reach a state where x is 2 and y is 3. So this violates the safety property. Okay? And this is quite typical that even though we started from some property that is really true of all the reachable states of the system, it is not inductive. And we have to strengthen it in order to make it inductive. We have to add some information about y, because the fact that x remains odd also depends on y, and on the fact that y is even. Okay? And if we do that, if we really strengthen the inductive invariant by also saying y is even, now it is really inductive, it is easy to see, and we verify the correctness of the program. And this is actually also quite similar to what happens in mathematics, where we try to prove things by induction. In many cases, we have to find the induction hypothesis, which is strong, in many cases stronger than what we really wanted to prove. Okay, so now the challenge for safety verification is how to find these inductive invariants. And this challenge consists of actually smaller challenges or sub-challenges. The first is actually even to specify the systems. How are we going to describe the initial state, the transition relation of the system, the safety property, the bad state, and so on. The second challenge is the challenge of deduction. Even if I give you a candidate inductive invariant, just checking whether it really satisfies the three requirements, this alone is typically undecidable because it involves checking implication. And the third challenge, and maybe the hardest, is really inference or synthesis, coming up with these inductive invariants. And now what I want to explain is how we approach it in Ivy from the point of view of supervised verification. So like I said, in supervised verification, we are trying to divide the task between the human and the machine. So what we do in Ivy is let the user take care of the specification. The user is responsible for describing the system. The machine is going to be responsible for the deduction. This is going to be done completely automatically. Given an inductive invariant, checking if it satisfies the requirement is going to be automatic. And the inference is going to be interactive. It's going to involve both the user and the machine. And to make this possible, we are going to use a decidable fragment of first-order logic to specify systems and properties. this will mean that it will be decidable to check inductiveness. This is why we can let the machine worry about deduction. This will be completely automatic. And it is a fragment of first-order logic, which means we will be able to use quantifiers, which will be very convenient in order to reason about unbounded number of threads, saying things like for every node or for every message. Another property of this fragment is that whenever we have a counterexample, we will also have a finite counterexamples. And having finite counterexamples means that we can display them to the user, and this is very important to carry on the interaction in the way we are going to do it. Okay, so, and then when we use this logic, we are going to, like I said, do the deduction completely automatically and interact with the user in order to come up with the candidate inductive invariants. And the interaction, again, is going to be based on graphical visualization of finite counterexamples. And another issue with Ivy is that even though it is based on logic, we use a logical fragment. We try to hide the logic when we can in order to make it more friendlier to users who are less comfortable with logic. Okay, and now let me illustrate how this all works in Ivy using a very simple example of a distributed leader election protocol in a ring. So I'll start by describing the protocol. So this protocol is run by nodes who are organized in a unidirectional ring. Each node has a numeric ID, and then the idea is that each node sends its ID to its immediate neighbor. Whenever a node receives a message with an ID, it passes it on only if the ID in the message is higher than its own ID. And when a node gets back its own ID, it becomes a leader. Okay? So this is the protocol. And the safety property is that the protocol selects at most one leader. Okay, so now let's see how we model this protocol in Ivy. Okay, so Ivy is based on first-order logic, which means that we think of states of the protocol as first-order structures, and we describe them using relations and functions that we can have in first-order logic. So, for example, here, so remember that I said that every node has an ID, which is a number. But here, we are using first-order logic, so we will not have numbers. Instead, IDs are just sorts. And we use a binary relation, a total order relation, to model which ID is greater than another. In order to model the ring topology, we use a ternary relation called between, saying that Y is between X and Z in the ring. We use an ID function that maps each node to its ID. In order to model the messages that are pending, we use a binary relation, pending, which tells us which ID is pending to each node. And we have a unary relation leader that becomes true for some node if this node becomes the leader. Okay. And the first three relations and function, actually, these are axiomatized in first-order logic. So I said that this relation, the less than, is a total order. We use axioms in first-order logic to express that. And also the between relation, we use axioms to make it behave like a ring. But if I have time, I will get back to it at the end. But for now, let's leave it at that. Okay, so this is how we describe a state. So now if we think of the state of this protocol, you see here we have a bunch of nodes organized in this way, and we see their IDs. Now the way we should think about it is like a structure in first-order logic. So you see that we have here 6 nodes. The nodes in the structure are represented by circles. We also have 6 IDs because each node has an ID, and the IDs are depicted here as rectangles. We have the ID function, which we depict here as edges from a node to its ID. We see the total order relation between the IDs. And here in this example, we have 2 messages appending for the node. This is actually node 5 here, even though its ID is 4. Okay, so we have these messages pending, and we can see really here edges showing that the ID 2 is pending to node 5, and also ID 5 is pending for node 5. Okay, so I hope the drawing is clear because I'm going to use this to illustrate the steps of the verification. Another comment, sorry, I didn't say. So the between relation, remember that it's a ternary relation, but in the drawings, I'm always going to draw just the immediate successor that we can derive from this ternary relation. So for example, here we only draw these edges, but in fact also we have in the between relation n5, n6, and 1, and basically every permutation here, and also n3, n5, and 6. Okay, so all of these are also in the between relation, we just don't draw them in order to make it clear. Okay, so this is how we describe a state of the protocol, and now how do we describe a step or a transition of the protocol? So we use actions. Here we have two actions, and the first one is ascend action, where a node n computes its successor in the ring, and I write it here in this way because this next is actually a formula in first order logic that can derive the immediate successor from the between relation. So, so the node n computes its successor, and then it updates the pending relation to include now a message from itself, from its ID, to this successor. A receive action. Receive is performed by a node n that receives a message m, and the message is actually an ID. This action requires that the message m is really pending for the node n, and the first thing that the node does is update the pending relation to non-deterministically either remove the message or keep it. Then if the ID of the node is equal to the message, to what it now receives, then it means that now it becomes a leader. It receives a message from itself, basically, so it updates the leader relation to true. Otherwise, if the ID of the node is at most the ID of the message, which means that the message has a higher ID than the node, then the node passes it forward, and this is again done by computing the successor and adding to the pending relation a pair saying that this message is now also pending for the successor. Okay, so this is how we model the protocol. And you see, we don't see much logic here. You would see a bit here, which I hid for you, but you don't see much logic. Logic is really a bit hidden. The protocol interleaves these actions in any order. And we want to verify this assert that says that for every two nodes, x and y, if both of them are leaders, then they are the same one. Okay, this means that there is at most one leader. Okay, just to illustrate a run of the protocol with these drawings. So here is a run that starts from this initial state where we have three nodes organized in this order in the ring. Initially, there is no leader, there are no pending messages. Now we have a send action where node 3 sends a message. So you see that now we have a pending message from the ID of node 3 to node 1, because this node 1 is the successor of 3. Okay, and then we have a receive action where node 1 receives the pending message, and because the ID of 3 is greater than its own, it passes it forward. So you see that now we have this pending message, okay, and so on. So this is just, sorry, to illustrate a run of the protocol. And an important aspect that I want to emphasize here is that here I show the run where we have 3 nodes. But when I modeled the protocol, I said nothing about the number of nodes. I didn't restrict it, it's not bounded. So actually the specification of the protocol is for any number of nodes, and this is also what we are going to verify, and this is what I wanted to say here. Okay, so this, you shouldn't be confused. We are verifying it for any number of nodes. Okay, and now to the actual verification. So the original paper that proposed this protocol also included a proof of correctness, but this was an informal proof in words. And the argument in the proof is basically that in order to become a leader, a node must get a message with its own ID, and this can only happen after the ID traverses the entire ring, so it means that it has to have the highest ID. And now let's see how we can formulate this correctness argument in Ivy using an inductive invariant that is specified in logic. So how do we turn it into a formal argument? So the safety property we already talked about. This is the safety property. And now we can verify this protocol with an inductive invariant that consists of the safety property and 3 additional conjectures. So the first additional conjecture is that if a node is a leader, then its ID is greater or equal than the ID of any other node. This means that the leader has the highest ID. The second conjecture that we need is when a message is self-pending, so you see when a message from the ID of N2 is pending for N2, then it again means that the ID of N2 is the greatest. And the third conjecture, and the most interesting one, says that messages cannot bypass nodes with higher IDs. So it says that if a message from N2 is pending for N1, and the way from N2 to N1 goes through N3, then it must be that the ID of N3 is not bigger than the ID of N2. Okay, otherwise the message could not pass. Okay, so this is the inductive invariant, but now how do we find it? Okay, so I just gave it to you, but let's see how we can find it. And now I'm going to tell you how Ivy tries to find this inductive invariant by interacting with the user. So here is how invariant inference works in Ivy. It's an iterative process. In each iteration, we have the model, the description of the system, and we have a candidate inductive invariant. Initially, it will just be the safety property, and we will add conjectures as we go along. The first thing that we do is check whether the candidate inductive invariant is inductive, and fortunately, we are using a decidable fragment, so this check is decidable. We can do it automatically. If the answer is yes, the invariant is inductive, we are done, we verify the safety. If the answer is no, then we have a counterexample to induction. And we find one that is minimal in the sense of a smallest number of elements in the domain, and display to the user. So minimality is mainly important to make it easy for the user to look at it so that it's not so big. And then based on this counterexample to induction, the user and Ivy together modify the candidate inductive invariant. Yeah. It could be. So I didn't want to get into that so much, but the user can define what kind of minimality he's interested in, and the options are basically the number of elements in the domain or the number of elements in that appear positively in different relations. So yeah, and then we can make sure that we find a minimal model in these terms. Okay, so this is the interesting part. How do we modify the candidate inductive invariant after we've found a counterexample to induction? So again, what is a counterexample to induction? A counterexample to induction is a pair of states where the first one, a pair of states that have a transition between them, and the first state in this transition satisfy the invariant, but the post state that we reach after taking the transition does not satisfy the invariant. Okay, this is a counterexample to induction, and recall, like we saw in the previous example, a counterexample to induction doesn't mean that the program is not safe. It is not a counterexample. It may just say that the invariant is not good enough, and what we can do when we get such a counterexample to induction is either strengthen the invariant to exclude this pre-state, like we did in the previous, in the while example, or we could also weaken the invariant to include the post state, like we do here, of the transition. So Ivy lets you do both, but today I'm going to talk just about the strengthening part. And strengthening in Ivy works by adding a conjecture, adding a new conjecture that says basically avoid this pre-state, this sigma. But we don't really want to avoid just this particular state, because we don't want to start excluding states one by one. So a key issue in this process is generalization. How do we generalize from a single state that we want to exclude to a set of states? And in generalization, what we are really after is finding some conjecture that will exclude this state, but will also capture something in the essence of the proof. This is what we are really after. And how do we do it here in Ivy? So here we use an idea from a previous paper, and this is the idea of using a logical notion of a diagram. So what is a diagram? So given a state, a structure in first-order logic, a diagram is an existentially quantified formula that basically introduces an existentially quantified variable for every element in the domain of the structure, and then encodes all the relations and functions between these elements using quantifier-free formulas. So let's look at an example. So we have this state here, this structure. So the diagram for it will have, and here we have two elements in the domain, the red one and the green one. So we introduce two existentially quantified variables. X is going to represent the red one, and Y represents the green one. And then, for example, you see that L holds for the red element. So we say here L of X. L does not hold for the green one, so we say not L of Y. We also have here a binary relation, and we see that it holds between the red element and itself. So we say here this formula less than XX, but we see that, for example, it doesn't hold from the green one to the red one, so we have not less than YX. Okay, so this is the idea of the diagram, and what does it give us? So the diagram is a formula that is satisfied by the state that we use to construct it, but also it is satisfied by any state that includes it as a substructure. And by substructure, I mean that we can take a part of the domain and then project all the relations on the remaining part of the domain, and we should get again this state sigma here. Okay, so for example, this sigma prime includes sigma as a substructure, because if I just look at these two elements and I project all the relations on these, I will get exactly sigma. Okay, and this state here, again, also includes sigma as a substructure, and it is also represented by the diagram, and so on. So basically, the diagram describes the state that we started from, but also infinitely more states. And a nice property of the diagram is that when we have transitions, like the total order, when we have relations, like the total order relation here, which are transitive, then the diagram has the effect of taking some interval here of length 1 and forgetting the length of this interval and letting it be any length that is greater than what we started from, which is a nice kind of generalization that we get here. Okay, so this is a natural way to generalize from a state to a set of states using an existentially quantified formula. And we can actually generalize even more if we decide that some of the facts or the information that we have in this state are irrelevant or not important for what we want to capture. For example, if I think that L here is not important, I can decide to ignore it when I define the diagram, this formula. Okay, I will just eliminate these literals that talk about L. I will get this formula, and this gives me additional generalization, where now this formula also represents this state, where you see here these red and green elements don't agree with the ones in sigma anymore. Okay, so it gives us additional generalization. Okay, so this is a way to generalize from a state to a set of states, and now if we want to exclude a state, we can just generate a diagram or maybe a generalized diagram, and the negation will say exclude this state. Okay, this is the idea. And what will actually happen is that we will find some counterexample to induction, which is a state. We will look at the diagram or a generalized diagram. We will negate it. This will give us a conjecture. And we'll do it over and over iteratively, which means that we basically exclude these shapes from the state space, and then the invariant that we will construct in this way will be this green area here. This is the shape of the invariants that we are actually generating here. And now the question that I didn't talk about yet is how do we decide which facts to remove when we generalize? I just said we could generalize more by removing facts, but how do we do that? And the way Ivy does it is by interacting with the user. This is where the intuition of the user gets into play. Okay, so now let me go back to the leader example, and let's illustrate how this happens there. And I don't want to go over the entire example, so I'm going to jump right into the third iteration and the last, which means that we already found these conjectures I1 and I2. And I want to find the conjecture I3, and let me remind you what these were. by looking at the first step of the iteration. So in the first step of the third iteration, we have our candidate inductive invariant, which for now includes a safety property, which means that we have no more than one leader. It also has the conjecture that the leader has the maximal ID, and it also already discovered the conjecture that says that only nodes with a maximal ID can have self-pending messages. This we already know. We already have it in our candidate inductive invariant. Now we are going to check inductiveness. And like we saw that the description of the protocol doesn't use logic so much, but Ivy has a VC generator that translates all the code to formulas, and then we can use satisfiability checking in order to check whether the candidate invariant is actually inductive. If the result is yes, we are done, but here this is not yet the case. So in this case, when we check whether this invariant is inductive, the answer is no, and we get a counterexample to induction, which looks like this. So let's look first at the post state, which is the violation of one of the conjectures. So in the post state, we see that the ID of node 2 is pending to node 2, even though node 2 is not, doesn't have the highest ID, right? Because the ID of 3 is greater. Okay, so this is a violation of conjecture 2, and note that it is not a violation of the safety property. Okay, and how did this happen? Why did we get the CTI? Because if we start from this state here, where a message from 2 is pending to 1, and we make one step of the receive action, then the message will be passed forward to node 2. Okay, this is how we get it, and you can see that this state here satisfies all of the conjectures because it doesn't have any leader, so the I0 and I1 hold vacuously, there is no leader, and also there is no self-pending message, so I2 also holds, but we see that in one step we get to a situation where we violate the conjecture I2. Okay, so now Ivy would show this counterexample to induction to the user, and the user will look at it, and what the user should understand is that this state is actually not reachable. It can never happen in a run of the protocol, because in order for the ID of node 2 to be pending for 1, it had to go through 3. Okay, the only way to get from 2 to 1 is through 3, but 3 has a higher ID. And this is exactly the property that we don't yet capture in the inductive invariant, and this is the property that you cannot bypass a node with a higher ID. So the user should understand that this is the issue, but now instead of writing it as a conjecture, Ivy will help the user get to this conjecture by basically just graphical visualization instead of actually writing it down. So how will this happen? So what the user will have to do now is, again, look at this example and tell Ivy what is really important in this example, for what facts are really important to keep in generalization and what facts are really not important. So one thing that is not important here is whether we have a leader or not. So the user will use these checkboxes and say, ignore the L relation. It's not really important. And let's say that the user also thinks that the between relation, the topology, is not important here. So it will uncheck this also. And now Ivy projects this state to the remaining relations, the one that the user decided to keep. And this is what we get here after the projection. Then we Ivy construct this formula, the logical diagram that represents this state and everything that extends it. And this is a candidate conjecture, but before we turn it into a conjecture, we want to help the user be convinced that, that they didn't generalize too much. And by generalizing too much, I mean that they didn't exclude a state that is actually reachable. And the way we do it is by using bounded model checking. With a bound that is determined by the user. So here, for example, we can use, the user told us to use bound 3, and we check whether this state, or the diagram, this state or any state that extends it, is actually reachable in 3 steps of the protocol. And when we do it, we see that because here we forgot all the constraints about the topology, this state is actually reachable. There is no reason that the idea of node 2 will not be pending for 1 if we didn't constrain the topology at all. Okay, so we see that this is actually a bad generalization. We generalize too much. We exclude a reachable state. We tell that to the user by showing a counterexample trace. And now the user understands that they generalize too much, and they can go back and now change the projection to keep the between relation. Okay, we saw that the topology is important here. So now we again project, but this time we keep the between relation and we construct the diagram. And like I mentioned before, because the between relation has this property of transitivity, then already when we construct the diagram, we forget about this concrete topology where this was 2 was the immediate successor of 1 and so on. And now it is just the interval between 1 and 2 can be of any length. This already happens when we just construct this formula. Again, we will help the user make sure that they didn't do a terrible mistake by bounded model checking. And here, when we do bounded model checking with the same bound of 3, we see that that's fine. Really, you cannot reach such a scenario, such a bad scenario, in 3 steps. And we get even more. We get a proof that you cannot reach this state or a state that extends it in 3 steps. And from this proof, we can interpolate. We can now see what was actually important for the proof. We actually use the answered core. And based on that, we can generalize even more. We can remove from the diagram everything that was not needed for the proof. And when we do that, we get this conjecture, which is exactly what we wanted. It is exactly this I3 that we were after. Then the user looks at it. The user has the final say. The user looks. The user is happy. So we add this invariant. And then, as I already told you, when we get these 4 conjectures, the inductiveness check succeeds, and we found the inductive invariant. And just to display this graphically, basically the shape of the inductive invariant that we found here is this. So this is basically some minimal description of the safety property, because it shows that we have 2 leaders. So this is a bad behavior, and everything that extends it is also excluded by the first conjecture that we have. Then this is a representation of the second conjecture. We see here that we have a leader, but the leader is not does not have the highest ID. So this is bad, and everything above it is also bad. Here we have the description of the conjectures that says that if a message is self-pending, then again, it has to be from then the node has to have the highest ID. So here it's a bad case for that. And this is the final conjecture that we now looked at. So these are all basically the diagrams that we excluded, and the invariant is what is left over here. Okay, so just to recap this notion of how we use supervised verification in Ivy. So you saw that what the machine took care of was inductiveness checks, which were decidable because of the fragment of first-order logic that we used. We also used bounded model checking, which again was decidable. We also did some weak form of interpolation using answered core. And all of these tasks were all decidable, which is a way to ensure that we have really predictable automation, that the user doesn't have to wait and maybe not get an answer. The user had to take care of the more creative parts in the process, but we used a graphical interaction in order to make it easier and natural for the user. Okay, so yeah, so this is formula, what I want to say about invariant inference. And how much time do I have left? If I have time left? Few minutes. Okay, great. So I can say a few words about expressivity. So far, I ignored it. I just say this is how we model this protocol using Ivy. But really, when we use this decidable fragment of first-order logic, it comes with restrictions. And then the question is, how do we also obtain expressivity, even though we restrict the kind of logic that we use? And there are really challenges involved in this. And the first challenge is actually just the fact that we use first-order logic, without even the additional restrictions of the decidable fragment. Even the fact that we use first-order logic is difficult because, for example, to specify the ring topology, we wanted to talk about paths between nodes of any length, which is some sort of transitive closure, which we cannot express in first-order logic. We had some sort of arithmetic. We had the original protocol that talked about the nodes as having IDs as numbers. So this is some sort of arithmetic, which again, we cannot express in first-order logic. But we saw that a way to avoid these issues or to overcome them and still manage to model the system in first-order logic was to use some domain knowledge and axioms. Okay, so now I can show you a bit more of the axioms that we use. So for example, the arithmetic part, we realize that we don't really care about arithmetic here. We just care about the total order between the IDs. So we use the total order relation, and we use some axioms to really say that it is a total order. We also had some axiom saying that the ID function is really unique. You cannot have two nodes with the same ID. And the most interesting part is really the between relation, which is a way to axiomatize the fact that we have a ring. So I'm not going to get into the axioms, but actually these axioms really are a way to define a ring. Okay, and in subsequent works where we wanted and did reason about consensus protocols and specifically about Paxos, we had additional challenges of this sort because in consensus protocols you usually talk about majority of nodes doing something. And this means that you also need set cardinality, so this was another thing that we had to overcome. And again, we did it with some domain knowledge and axioms. Specifically, we used quorums and we axiomatized the fact that two quorums have to have a common member. So this is one sort of challenge. And we have another, which comes really from the specific fragment that we use of first-order logic, which put in particular restrictions on the kind of quantification that we use. And this is something that we also dealt with in this paper, and I'm not going to talk about it here, but we have a way to also overcome this in certain cases. Okay, and with this technology, we managed, I go back to the table that I showed you earlier, so we managed to verify all these protocols, including several variants of Paxos, and now I can also talk about the numbers. So the column here shows you the size of the model, how many lines of IV we needed in order to model the protocol, and here you see the sizes of the invariants, the number of literals. And this is what the user was involved in generating. So you see that it's much less than what you would have to do if you try to write it in Coq. Okay, so just to summarize, so what I showed you here is how we do safety verification in a supervised way by letting the deduction be handled completely automatically by the machine and letting the inference be done interactively by both the user and the machine. And the interaction was done using a graphical user interface. We saw that how we use the decidable fragment of first-order logic in order to really make the deduction decidable, and also to make sure that we have finite counterexamples that we can display to the user as a basis for interaction. And it's surprisingly powerful, even though we use a decidable fragment of first-order logic, which is quite weak. We managed to use it to verify really interesting protocols, state-of-the-art protocols, consensus protocols such as Paxos and many of its variants. And I didn't talk about this, but we have a recent work where we also go beyond safety and we can verify any temporal property. And for future work, I would like to look at more distributed systems and specifically realize what kind of logics we would need in order to handle them. Can this logic be enough if we accumulate enough domain knowledge and axioms, or do we need something else? What kind of interaction would be suitable maybe for other logics or for other protocols? What kind of other inference techniques could we use? Hopefully, techniques that are even more automatic. Here, in what I described, the user is involved in generating every conjecture. Some of the conjectures should be easy to infer automatically, so adding some more automation to that. And also a very interesting question is really what are the theoretical limitations of this approach? So far, everything that we try to model in Ivy with some tricks and derived relations and domain knowledge and whatever, we succeeded, which of course doesn't mean that we could verify everything, but it's really interesting to understand the limits. And just the last thing, I'm looking for postdocs and students, so if anyone is interested, please contact me. And this is the beach of Tel Aviv, which is where you could be sitting and typing. Okay, thank you.
Thanks. Any questions?
Yeah, I'm just curious how you count the annotation overhead. So for instance, I mean, the various clicking that you do in the tool, is that overhead for the user? And also the axiomatizations that you described were partly problem specific. So that's also overhead you have. So is that included in your 1/10 on the slide, or how do you do that?
No, so yeah, the 1/10, yeah, this is a very good question. How do you measure the user effort without conducting a user study, which we also had some workshops in the university where we let students use that, but we didn't do a formal user study, so we didn't do that. And therefore, the way we currently measure the user effort is really by counting the number of literals that were in the conjectures, which is really not counting the number of clicks. We think that even if you look at the number of conjectures, each conjecture is a step where the user is involved. But usually, each step is not that difficult because you look at some counterexample, you click, you do some things, you accept or you reject. So we think that this is a reasonable measure. It's definitely not the best, but for now, this is the way we measure it, just the number of conjectures. Yes, and this is also a great question. So for now, for example, the total order relation is something these axioms that we use all over. In everything that we model, it's very useful. The between relation was really specific to this example, but in many cases, we see that these axioms are actually reusable. So maybe it's really for a problem domain. For example, when we worked with Paxos and it's a different variant, maybe it's not surprising that we just needed these axioms of the quorums. But once we had them, we used them across all variants. So maybe if we really look at another family of protocols, we would need other axioms, and this is really something that we don't measure when I talk about user effort, but I think that they are reusable to some extent. So,
sorry, I don't think I got it. So you are verifying the model that you build in Ivy?
Yes.
So how far it is from an actual implementation of that protocol?
So this is the next step that we are working on now, which is really to derive, to extract an implementation from the code that we have in Ivy. So currently, the kind of code that I showed now is quite far because, for example, the messages were just modeled as a pending relation, which doesn't even keep track of order or anything, but this is just an abstraction. But we are working on more low-level representations, modeling of protocols, and then really extraction of actual running code from them in order to close this gap.
So your generalization heuristic only gets you universally quantified invariants. What are your tricks for having Shoham functions? If your inductive invariant requires existentials?
Yes, so in this work, you're completely right. In this work, we just generated universally quantified invariant. And currently, we don't have any work where we actually generate invariants that go beyond that interactively. So for them, the user would just have to type in the conjectures, which is, again, possible. And again, you get the benefit that the deduction is done automatically and that it is decidable as long as you are in a decidable fragment.
Well, first a comment. I think your picture of the beach is totally fair because every time someone from Zurich gives a talk, they always have a picture of their mountains and lakes, so good job. Have you considered trying to encode Pamela Zave's chord proofs using Ivy? That might be an interesting case study because the kind of end-to-end argument involves a probabilistic argument that the ring has a certain structure, and I was a little confused how that might fit into your framework.
So I'm not sure I understood the problem. Are you asking about a proof of some probabilistic properties, or?
No, the chord DHT
Yeah.
had some flaws in the original paper, and Pamela Zave has sort of systematically gone through and found the right invariants for proving it, but part of her invariant involves a probabilistic argument about the structure of the ring.
Yes. So
I suppose you could just axiomatize that and then do the rest of the proof in IV.
Yeah, so I don't remember the full details of that, but we definitely used Pamela Zave's modeling in order to carry out the proof in IV. But I don't know to say exactly, I don't remember the details of that so much. But it was all based on her modeling, so.
Questions? I had one question, like in the counterexample thing. Can you generalize it to sets of concrete counterexamples, not just one?
You mean show the user a set?
Yeah, like combine when you generalize to kind of take set of concrete ones instead of one, because otherwise you have to do backtracking, I guess, right?
Backtracking would be the weakening.
Yeah.
Yeah.
No,
So
if you go down, you fail to prove it, you have to backtrack because he may have failed with the generalization.
because you generalize too much. Yeah. So for now, generalization considers one state at a time. That's it. We do bounded model checking in order to sort of help the user be careful not to generalize too much in order to prevent this need for backtracking. But yeah, definitely looking at multiple count. So you're basically saying look at several counterexamples in order to find some property. Really, if you're like the common, right, the common property that you can get out of it. So this is a great idea. We don't do it for now.
Okay, if no more questions, so let's thank Sharon again.